All right, so thanks everyone for watching this presentation today. Whether or not you're watching from the CSCI 2020 conference, 2020 has definitely been a crazy year so far, so very happy we still get to present our work even if it is in a digital format. And so today what we're going to be talking about is an efficient localization for indoor environments using classification algorithms. Now, I know that sounds like a mouthful, but our overarching goal here really is just improving the positioning accuracy of a user's device in an indoor location. We're going to do that by implementing two different machine learning models, one a decision tree model and another a recurrent neural network, long short-term memory, or for short, RNN LSTM. And in the end, what we're going to do is we're going to benchmark the performance of these two up against each other. So in today's technological climate, there is a huge demand for indoor locationing-based services, and in the past, the data for these services came from the Global Navigation Satellite System, which you could just basically refer to as GPS. But the problem with this is that information from the GNSS worked well for outdoor environments and didn't work very well for indoor environments, and still doesn't. And for a couple of reasons listed here. Number one, signal interference in surrounding radio sources. And another one is physical obstructions, such as multi-floor buildings, walls, ceilings, etc. And so what these can cause are issues like multipath propagation, where basically you have a transmitter and a receiver. Transmitter is trying to send a radio signal to a receiver, and because of physical objects being in the way, the signal basically breaks off into two different paths and ends up arriving at the receiver with two different signal strengths, basically leading the receiver to believe that the signal came from two different locations when in fact it's actually from the same source. So what has industry done thus far to improve upon positioning accuracy? Well, one of the big concepts right now is called Wi-Fi fingerprinting, and it's kind of the one we'll be focusing on today. But if you don't know what it is, basically think of it like this. Let's say we have a square grid, and inside this grid we have just a bunch of random predetermined coordinates. And I'll draw a little wireless access point down here. But basically at each one of these predetermined coordinates, we want to have a device that transmits a radio signal back and forth between itself and the wireless access points. And this is going to essentially derive an RSS value, or receive signal strength, it's just short for that. And then what happens is this RSS value is then paired with the location coordinate here at this point. And that pair then, and forgive my awful attempt at being an artist here, but that pair then of that coordinate and the RSS value is essentially like a key value pair almost. That is then stored in this repository, this RSS repository. So what happens then when an application ends up going live, the RSS values from an actual user's phone then is derived, and then that is mapped to an RSS value in the repository, and then the corresponding coordinate is the estimated location then of that user at a given point in time. So given this information, what are some common issues with Wi-Fi fingerprinting? Obviously, it's going to take a significant amount of time and effort to collect an RSS repository, because if you think about, for example, trying to map out a university campus, it would take a significant amount of data points to be able to accurately represent and model an entire university. Not to mention different platform devices are typically going to produce fluctuating RSS values, because if you consider a iOS Apple smartphone versus some flavor of Android, they're typically going to have different hardware architecture as well as software and operating system architecture as well. And so when it comes to Wi-Fi based fingerprinting, there's basically two different parts. There's the offline phase, which is the part we talked about where you kind of build up that RSS repository. And then there's the online phase where you then take a user's device in real time and map the RSS value coming from their device to an RSS value in the repository and essentially estimate their position by using the corresponding coordinate as their predicted position. And so the list here just kind of shows past experiments and advancements people have made in different areas of Wi-Fi fingerprinting. I don't necessarily want to go through this list exhaustively, but the point I want to make here though is that there is a lot of research going on in this field right now and on basically how can we make Wi-Fi fingerprinting more efficient? How can we create better classification and prediction models? But all these advancements aside, the one area there hasn't really been a whole lot of improvement on, or at least as much as industry would like to see, is the issue of fluctuating RSS values due to differing platform devices. And so why are we comparing a decision tree up against an RNN LSTM? Well, it's been shown in past experiments that the RNN LSTM can actually provide some pretty good positioning accuracy with Wi-Fi based fingerprinting. But in every machine learning application, you're going to see this trend where you want to basically benchmark a computationally complex model, in our case, our RNN, against a more baseline model. And in our case, that would be our decision tree model, because decision trees are pretty representationally simplistic. And so the overarching goal then is, or idea is, that if we get the same or better or even insignificantly less performance from the decision tree as opposed to the RNN, well, then there might be room there for a trade-off where we say, okay, well, let's sacrifice just a slight bit of performance, or even maybe gain some performance for using a visually simplistic model like a decision tree. And again, that's another trend you'll see a lot, where sometimes you sacrifice performance for representational simplicity. And so what we're hoping to do with our proposed approach design then is sort of reduce that variance in data due to fluctuating RSS values. So at a very high level, our experiment is broken down into two parts here. In part one, we basically just input the raw data, our raw training and test data sets, and then we train our models based on this raw data, so our decision tree and our RNN LSTM, and then we test those models and then compute the error of those models. And the error is just the location that our models predict the user is at and their actual location. So it's the difference in distance between those 2 points. Part two is basically structured the same way, except in between the input and train steps, we have a normalization step where we basically normalize all the RSS values, hence reducing the variance in the data. And you can see down here at the bottom kind of how our each sample is set up. So we have our X coordinate, our Y coordinate, columns 1 and 2, and then the next 9 columns are representing the RSS value readings coming from each of the local wireless access points, given that the device is at the coordinate, in this case, it'd be 6, 17. And so let's kind of take a look here now under the hood of what's going on during all of these different steps. And during the input step, we have 5 different platform devices that we're using. Each platform device is going to produce a train data set and a test data set. And this is raw data here. We haven't normalized this yet, and this is all being input into MATLAB. And so kind of looking past part one here for now, in part two, we have this normalization step, where basically we're taking the raw data sets individually, so the training and all the training and test data sets individually, and we're inputting them into this normalization function. And what the normalization function is doing is it's going to standardize and normalize each RSS value in a data set individually. And so our normalization function is basically we take the current RSS value being considered and subtract it from the mean of the RSS values as a whole in the entire data set, and then divide it by the standard deviation of the RSS values in that same data set. And then once we have all of these normalized RSS values, we basically re-vectorize them and then input them back into the program to then train our models with now on this normalized data, as opposed to part one where we would just train them on the raw data. And so when we go to construct our decision tree now, we're actually using MATLAB's fitc-tree function with its default training parameters. And so by default, when MATLAB builds decision trees, it uses the standard CART algorithm along with the split criteria of node impurity, so a measure of node impurity at each level, and it calculates the node impurity using Gini's diversity index. The max number of splits it allows in a tree is n-1, where n is the number of samples in a data set. So our training set, for example, at 2,000 samples, it would allow a total maximum of 1999 samples total, or splits total rather. And Because of that, it tends toward to build deeper trees, which can cause overfitting. But the good thing is that MATLAB actually optimizes its splitting algorithm, and it tends to favor full trees, so sort of avoid that worst case scenario of having a tree that is of depth n-1. And so to get a little bit of a better example of how our decision tree model is actually deciphering and figuring the user's estimated location, let's take a look at this diagram here real quick. And this is a bit of an oversimplified example, but just imagine with me here for a moment that we have this very narrow hallway, and these white lines or walls are the walls of the hallway. And at one end of the hallway, we have a wireless access point here. And these boundaries are representing at a certain distance away from the wireless access point, what are the RSS values that this wireless access point is transmitting back and forth between itself and a device. So obviously, for example, at the first boundary here, we have an RSS value equal to 2. At the second boundary, it's an RSS value equal to 4. Third boundary is 6, and finally, this last boundary here is 8. And so you can see that our device is transmitting an RSS value of 7.5, and we're kind of in this final, in this last area here on our diagram. And so since our RSS value is equal to 7.5 and we're kind of in this boundary space here, our estimated position, or the estimated position of our device, is going to be 1, 4. So that final predetermined dot on the diagram. And the reason for that being, let's say we come in here to the decision tree, and based on the rules, we say, okay, is our RSS value that we're transmitting, is it greater than 4? Well, in our case, 7.5. So yes, it is. So we go to the right. And we say, is our RSS value greater than 6? Yes, it is. So we go to the right again. And that's how we come up with our estimated position of 1.4. You can see then that all of these rules then are sort of relating back to the boundaries here on our diagram. These little green boundaries. Because we have RSS value equals 2, 4, and 6. And that's exactly what the rules in the decision tree are checking for. Now, in the case of our experiment, we had just over 2,000 records with 9 features per record. So things got pretty complicated pretty quickly. And this is just a snapshot of a segment of one of the decision trees that were made during our experiment. And just point being that these decision trees can get pretty complicated and pretty extensive fairly quickly. So now when we go to create our RNN LSTM model, we use MATLAB's train network function. And this time, though, we actually modify and we create some custom parameters for the RNN LSTM. The good thing about RNN LSTMs is that they are good on temporally sensitive problem domains. They carry cell state and memory, so they can reference back to earlier time steps and data from earlier time steps. And they also have a carry state thanks to the LSTM variation of an RNN. And remember how we talked about that the LSTM variation kind of helps diminish the vanishing gradient problem. And we'll see that here in just a little bit. And so here's some of the custom model parameters we set for our RNN LSTM, where we put the input size equal to 9, because we have 9 wireless access points, so 9 features. We set the number of hidden units or nodes to 180, the number of classes to 105, since we have 105 predetermined coordinates on our grid. Epochs is set to 300, so the training model will run, or I should say the training data will run 300 times. Our learning rate we set to 0.01, and our optimization function we have set to the atom optimization function. And so in this diagram to the left here, we can kind of see how information moves through these LSTM layers in MATLAB. And the LSTM layers kind of divide the sequential data up into these different time steps. And so the X vertices here are representing the input at every time step, which would be, in our case, our 9 RSS values coming from each wireless access point. And the H vertice here is basically representational of the output every time step. And it's important to note that the output of every time step is actually the input to the next time step. So if we take a look at what's going on under the hood here of one of these LSTM blocks, we can see that we have the output from the last time step being input as the hidden state or input to the current time step. We have the X, which is representation again of the input, so the RSS values of the current time step. And we have this new symbol here that's a C, and what this is basically the carry state. What the carry state does is you can think of it as like a giant conveyor belt that's carrying information to all the time steps from all the previous time steps. And at any moment in time, the current time step can then access this information and kind of help build long-term dependencies and associations with data in earlier time steps. And so what these letters are here are in the middle are just gates. So we have our forget gate and our information gates, and then our output gate here. And basically the responsibility of each of these gates is that the forget gate will basically reset data in the carry state here, so our C, that the LSTm layer no longer deems relevant. The information gates in the middle G and I will add new information that is deemed relevant, and the output gate O will basically control what information from the carry state, so our C, is able to manipulate data in our hidden state H, or our new output data here. I know this all seems very arbitrary, but the important thing to take away from this is that at the end of the day, when all this information makes it through to the end of our LSTM layer, this final state is just going to be basically a bunch of probabilities that are representational of the probability that a user is at a certain location of one of our predefined classes, meaning our coordinates in this case. And so during our test step now, we are able to input our test data sets into each model, both the decision tree and RNN LSTM, to allow them to make predictions then on all the samples in our test data set using the predict function for the decision tree model and the classify function for the RNN LSTM model. And so now finally we come to the step of calculating the error in our prediction, or I should say the prediction of our models. And we do that by using the Euclidean distance formula. So basically what we're doing is we're trying to find the distance between the predicted location we thought the user was at and the actual location that they're at. And then ultimately what we do is we end up adding up all of these errors amongst all the different test runs and then averaging them to get the average error of each model. And that's done individually for part 1 and part 2 of the experiment. And so part 1 of the experiment, we can see that our decision tree model greatly underperformed our RNN LSTM model, since the average error for the decision tree was about 3.715, whereas for the RNN LSTM was about 2.3355. And you can see below here the scores of each test run. So we basically ran each test set with each training set in both models. This is just a better way to sort of visualize the error rates for each model in part 1. And don't let this deceive you, because you have to think here, the scale of our decision tree model here of the graph is much greater than it is here. So at first glance, it looks like our decision tree outperformed our RNN LSTM by a long shot, but that's actually not the case. And so in part 2 then, when we first normalize the data, you can see that then our decision tree actually had a much better performance actually than our RNN LSTM model did. And again, we've displayed the scores here below. Now here the scales are a little bit more similar, so it's a little bit harder to sort of misinterpret this, but just another way again to visualize the error rates for each model. So we saw in part 1 of the experiment that our decision tree model was actually greatly outperformed by the RNN LSTM model. This really comes as no surprise, seeing as decision trees do not do well when there's a high variance in data, and seeing as we didn't normalize the RSS value data sets in part 1, there's really no wonder why our decision tree model underperformed so much. Okay, so then in part 2 we did normalize the data, and our decision tree did in fact outperform our RNN LSTM. So at this point we need to question, how could something as computationally complex as an RNN LSTM be outperformed by such a simplistic model as a decision tree? Well, computational complexity does not always tell you the whole story. When it comes to machine learning, you don't build models to generalize well to every problem domain. You actually engineer models to solve a particular problem. So RNN LSTMs do perform well in sequential data, but more so when there's like a global dependency of the data, where local data, or I should say recent data, matters more than data from a long time ago in the past. So if you think about trying to predict a yearly cycle of temperatures and you want to know what the temperatures are going to be for the next week, well, if you input data where the last 3 weeks have been trending warmer, but 3 months ago it was below freezing, your RNN LSTM can pick up on patterns and realize that, okay, 3 months ago temperatures were sub-zero and the last 3 weeks have been trending upwards, meaning warmer. So I can only assume then that it's, spring or summer, and I can assume then that the weekly forecast is going to be trending warmer as well. Whereas in the case of our experiment, we have situations like this where we have our coordinates that are staying relatively constant on the x-axis but trending downwards on the y-axis towards 0, and all of a sudden it skips over here to where x equals 15. So in this case, our recent data really won't matter as much to predict this because it's a totally different, I should say that from time step to time step between these two, it really won't gain the RNN LSTM much information. So it's variances like that that can break patterns in RNN LSTMs. And so another thing to consider too is that MATLAB does in fact optimize, or at least tries to optimize its decision tree algorithm as much as possible by favoring full trees, which can kind of help eliminate that worst case scenario of having n-1 depth for its classification trees. And so in conclusion, we can say then that if there's no sense of normalization, or there's a large fluctuation in RSS values, a decision tree model probably won't be the most reliable model when doing or when implementing with Wi-Fi fingerprinting. But on the other hand, if data is first normalized to where we can reduce that high variance in data, then a decision tree absolutely can be considered a reliable model. Just a little food for thought here. The approach we took to some of the model settings and parameters at the beginning were a bit of a naive approach. So I think it'd be worth extending the research to configure and maybe play around more with some of the training settings and parameters that we feed, at least into the decision tree, but also into the RNN LSTM. And also increasing dataset size, because normally, or oftentimes I should say, neural nets perform much better with the more data they're fed or given. And also maybe implementing or including hybrid approaches such as a CNN, so a convolutional neural network with an RNN LSTM. That way the convolutional neural net can derive local features of time sequential steps, and then the RNN can just kind of look at a global association of all those features together to maybe pick up on patterns. And that brings us to the end of our presentation. I'd really like to thank the CSCI committee for giving us the opportunity to present here at this conference. And I'd also really like to thank Dr. Rouse, Dr. Gafour, and Dr. McDede for all of their guidance and also work they've done on this paper and this research. So thank you very much.